Okay, so everyone can hear, can see the slide?
No, I can't see.
You can't see. See the slide now?
Yes.
Okay, good. Okay, guys, do you receive any email from your from the college when you can go for a practical and everything? Do they inform you anything? Nothing. Anybody? No.
I think yes. Wait.
So when they said you go ahead with the face to face?
18.
18, 18 of February, right? 18 of February, you get your practical, right?
Yes.
Practical. Okay. You see, still discussions going on. Okay. So let's go to the Word file first. Okay, so about capacitance, we talk about the initial part, 70% of the topic done. We done what is meant by capacitance, the symbol, how charging happens, discharging happens, and we talk about some questions. Then recently we talk about series parallel, the capacitor connected and series and parallel, how the total charge, total capacitance will arrange themselves. Okay, in series, in parallel, we found to be the capacitance is the highest, increases. The capability to store charge is a lot. Okay, and if you connect in series, what happened? So the total charge is the same for everyone, and capacitance decreases. Less capacitance. Capability to store charge become lesser. Okay. Then that day we talk about this one circuit. Few circuits we discussed, and how to solve it to find each charge stored and total capacitance. Okay, so today we're going to talk about energy in capacitor. Okay, so we go back to the slide. Okay, energy stored in a capacitor. So when a charge flows and charge is separated, energy is stored in the capacitor. Okay, how energy is stored in the capacitor? You need to include this in your notes. Okay, this is not in your notes, but I tell you, what causes energy stored in the capacitor? By doing work to separate the charges. Doing work to separate the charges stored as energy in the capacitor. Okay, for example, let's say you have a positive and a negative charge together. You bring the negative further away. Work is done by you. Okay, the amount of work done to separate the charges is stored as energy in capacitor. Please put in your notes. What causes energy stored in the capacitor? By doing work to separate the charges. Okay, by doing work to separate the charges, that work is stored as energy in the capacitor. Okay. So yeah, a charge capacitor store electrical energy with equivalent to the work done. Yeah. So you see, the battery, we talk about the battery. Battery, if you plot V versus Q, okay, how the graph going to look like? It's a constant straight line. Okay, the voltage of the battery is constant. So the charge release, so the area in the graph, this is the energy released by the battery. Okay, the work done to transfer the charge by the battery is QE. The total amount of energy released is QE. But for capacitor, for the case of capacitor, how's the V versus Q graph looks like? V versus Q graph for the capacitor, it's a straight line like this. The voltage increases from 0 to the peak voltage of the battery. So the energy stored in the capacitor is the area under graph. How much? half QE. Okay. However, PD across capacitor increases from 0 to V, 0 to V. As charges are being deposited, hence effective average PD is half V. So therefore, the energy stored in the capacitor is half QE. Battery releases QE, but capacitor store charge half QE. What is the efficiency of charging the capacitor? What is the efficiency of charging the capacitor? Anyone? How many percent? 50%. 50%. Whenever any energy charging the capacitor, only 50% efficiency. 50% stored in the capacitor, another 50% in exam they will ask what happened to that another 50%. Another 50% they say it lost as heat energy in the connecting wires. 50% of energy is lost as heat energy in connecting wires. Okay. But the quite not say funny lah. Always 50% lost. Only 50% stored. So half QE is the energy stored in the capacitor. So this is the energy formula for capacitor. How much of energy is stored in capacitor? Half QV. So you know C equals to Q over V. Okay. So if you throw out the Q, substitute CV, you get half CV squared. Okay. You throw out the V, substitute Q over C from this formula, you get half Q squared over C. So energy stored in capacitor, you have three formulas. Half QV, half CV squared, half Q squared over C. The last formula in this topic. Okay. The energy stored, half QV, half CV squared, half Q squared over C. Which formula to be used? Depend which information is available. C, Q, V. You know Q and V, so first formula. You know C and V, second formula, and so on. Okay. So C is in farads, Q in coulombs, V in volts. Energy, of course, in joule. Okay, so one example. So what is energy stored of a capacitor? Half QV, half CV squared, half Q squared over C. Okay. The first question. Find the charge and the energy stored by a 1000 microfarad capacitor, and the potential difference is 6 volt. Okay, which formula you can use? 1, 2, 3. Which one is easiest? So you know C, you know V. So we go for the half CV squared. Use half CV squared, you get the energy. Okay. So yeah, or you can find the charge first, half CV squared. Put 6 squared. Capacitance 1000, but it's microfarad, change to farad, and 6 squared, so you get the energy. Okay. Then if it's 12 volt, you put 12, so it's 12 millicoulomb of charge stored. This charge stored, energy stored is 72 millijoule of CV squared. Okay, this is a direct substitution of the formula. Okay, another one example, guys. Come on. Read the question. 1 minute for you to calculate. Okay, so got the idea. 47 microfarad capacitor in a flash gun supplies the average power of this for this time. What is the potential difference across the capacitor before it is discharged? So energy equals to, because C given, you want to find the V. So what formula to be used? Half CV squared to be used. Now do you get the energy? The power times time is the energy of the energy stored in the capacitor. So the solution is half CV squared must come to your mind because you are looking for V and C is given. So half CV squared is the most suitable energy formula to be used. So PT is half CV squared. So therefore we find the voltage. It will be 92.3 volts. Okay. So yeah, so this is the energy formula. Any part you don't understand? Okay. One. So if you plot V versus Q, if when the capacitor storing charge, the voltage rises. Okay, the area in the graph is the energy stored. When you go from let's say from 0 you go to 1, go to V1. This is the energy stored. The area in the graph, energy stored. The capacitor charge from V1 to V0. Okay, this trapezium is the energy stored. Okay, so let's say the capacitor from V0 discharged to V1. The energy release will which energy? Again the trapezium. V0 to V1. So everything is about the area in the graph of V versus Q. Okay. When V is plotted against Q for a charging capacitor, a straight line is obtained. Area in the graph is the energy stored in the capacitor. V versus Q. Remember. So work done depending on a small charge Q, energy stored. Therefore, for charging a capacitor 0 to Q0, this the energy need to be stored. Okay. You see above one example. There is one capacitor charge from voltage 0 to 10, and the charge stored was 5 microcoulomb was stored. Okay, so what is the capacitance of the capacitor? So V versus Q. What represents capacitance? C equals to Q over V. So the gradient, find the gradient. Then what? What is your C? C is reciprocal of the gradient, correct? Reciprocal of the gradient is your capacitance. Or you can take maybe one coordinate. You can take one coordinate, Q over C, Q over V also will give you the capacitance. In this case, capacitance is 5 times 10 to the power negative 6 coulomb of microcoulomb of charge, 5 times 10 to the power negative 6 coulomb of charge stored, and voltage is 10 volt. So capacitance means amount of charge stored per unit volt. So divide by 10, so you get the capacitance. So sketch a graph for energy stored against charge. So energy stored against charge. So energy against charge, you use E equals to half QV. So if you use E equals to half QV, E versus Q, E versus Q, okay, E versus Q, right? Sketch a graph energy stored against charge. You draw E versus Q. You can't use E versus Q. You can't use this formula. Which formula you can use to plot the graph? E equals to half Q squared over C to be used. This formula to be used. When you want to plot what versus what? E versus Q. Why you choose this formula? Half Q squared over C. When you want to suggest the E versus Q. Anyone? Why we can't use half QV? Why you can't use E equals to half QV to sketch the graph? E versus Q. Anybody? If you use E versus Q, the remaining data must be constant, right? When you check
Yeah.
independent, dependent, the other remaining must be constant, right? So half Q squared over C, the half and C is constant. So yes, we can use this formula. If you use E equals to half QE, can you sketch E versus Q? You can't because B also changing. So it's not constant. So you can't use predict by using this formula. So if you use E equals to half Q squared over C, E and Q squared, so how going to, the graph going to look like? Going to look like a quadratic as shown here. E versus Q. It's a quadratic graph. It's a quadratic. So E versus Q is a quadratic graph. Okay. How E versus V you can plot? What formula you use to plot E versus V? Which formula, energy formula to use? E equals to half CV squared to be used. I think always use the C one. C is constant. So you plot E versus V, also you're going to be a quadratic. E versus V also quadratic. Okay. Sketch the graph energy stored against charge. What shape would the graph energy against PD would look like? So these are the two answers. So remember, when you want to sketch graph, use energy formula involving C because C is constant. They need to be constant. Any questions from here? Question.
So the shape I just say like it's a curve, is it?
It must be a quadratic, right?
Yeah, but what? How do I say it in words?
The shape, you just sketch the graph.
Or I just sketch the graph? No, I just state the shape.
You just draw a curve, and you want to put it as a quadratic. Normally they ask you to sketch graph. So sketch graph, you draw a quadratic curve.
Okay.
Okay, you know the quadratic curve, right? Like a semicircle. You draw this only for the positive side. Draw this, understood? Yeah. Okay, so that's about energy stored. But now, when a capacitor is charging, some energy is lost. As I told you, how much energy is lost? Exactly half QV lost. So the energy loss is exactly half QE. So if the total charge supplied to the Q is Q naught, the EMF of the battery is V naught. So battery releases Q naught V naught, but capacitor store half Q naught V naught. So half lost. Where it lost, hence energy loss as heat in the connecting wire. Remember, they'll ask reasons. Where? What happened to the lost? Lost in where? Lost around. Lost across the connecting wires as a heat energy. That's the blame we do. Okay, so now one example again, 1 minute for you. Read the question, try to predict the answer. Of course, the next slide is the answer. Don't switch to next slide. Read the question, try to do yourself first, 1 minute. Okay, so you get the first answers. The resistor and the capacitor are connected in series. This is the charging circuit. So they said at one particular moment, the current flow in the circuit is 210 microampere. The current flow is 200 microampere. Is it the capacitor completely charged or is halfway charging? It's halfway, right? because completely charged means current flow becomes zero. So it's halfway charging. Halfway. The process of charging lah. Halfway. Calculate for that instant what is the PD across the resistor. The 20 kilo ohm, the current flow is 210 microampere. What is the PD across the resistor? VR how much? So what formula? I times R, right? I times R will give you the voltage across the resistance. So 200 microampere times the resistance 20 kilo ohm will give you the VR. Correct? So VR is equals to I times R. How do you got PD across the capacitor? So the EMF is equals to what? VC plus VR always what? So second, how do you get the VC? Is the EMF minus the VR. Give you the PD across the capacitor. Okay. Hope both of you, all of you have this idea in your mind to get the VR and VC. Okay. Remember, the time increases. When the time increases, which V increases? VR increases or VC increases? And when you continue running this circuit, okay, the VR increases or VC will increase? VC will increases. VR will start to drop until when the time completely charged, VC become maximum to 6 volt, VR becomes 0. Okay, so that's the first answer. So V equals to IR will give you 4.2 volt. So V across capacitor is 6 minus 4.2 volt. So 1.8 volt. Okay. So when the capacitor has become fully charged, what is the energy stored in the capacitor? The energy stored in the capacitor is just half CV squared, because we know C, we know C 100 microfarad. We know V now. We know V at that moment 1.8. Oh, sorry, we know 6. So we can find the half CV squared is the suitable formula. So 1.8 times 10.83 joule is stored in capacity. Okay, what is the total energy taken from the battery? Definitely 2 times of the energy stored in the capacitor. Just times 2. Energy stored in the capacitor times 2, you get the energy released by the battery. Exactly 2 times greater. The energy released by the battery. Okay. Any part you don't understand here? Don't understand. Okay, good. So hope everyone can understand the concept. Okay, so another question. There is a circuit with resistor, got 2 capacitor, one 2 microfarad, another one is 4 microfarad connected in series. There is a switch here which open at the moment, 12 volt. Question is, the circuit shown, calculate the energy stored. The 4 microfarad capacitor. The switch S is closed. Then the switch S is open. Yeah. If I show you the solution, 1 minute again. Guys, come on. Try to think how to get the answer. Calculate for me before we see the solution. Get some idea in your mind. Calculate. Try to calculate. Think about what formula to be used. 1 minute for you. Okay, so I hope some of you got answers. So when the switch is closed, the switch here is closed, the current will flow here, here, and where it flows. It flows past to 2 microfarad, or you go to the switch.
Switch.
Go to the switch. The current will go to the switch and pass the 4 microfarad. So 2 microfarad is like a waste. It won't pass through 2 microfarad because at some factor opposing the current is there, so it won't flow. It will go to the path where no resistance. So when switch is closed, so the 4 microfarad is the only capacitor in the circuit. So the 4 microfarad, when completely charged, the 4 microfarad, what is the maximum voltage you're going to utilize? You take the entire 12 volt, right? Because the 2 microfarad is not in the circuit anymore because you have a short circuit. So 2 microfarad current won't flow. So the total capacitance of the circuit is only 4 microfarad. So therefore, when switch is closed, what is the energy stored in the 4 microfarad? Which energy formula do you use? Do you use half QE, or do you use half CV squared, or do you use half Q squared over C? Which one is suitable? One. So you have the charge 4 microfarad, you know the voltage 12, so we use half CV squared. Half CV squared to be used. So you can use half CV squared, where C is 4 and V is 12, and you get the answer. Okay, that's the first one. And as it's closed, 4 capacitor is charged, the energy stored is 288 microjoule. The C is 4, the V is 12 exactly. Okay. Okay, the tricky part is part B. When the switch is open, when the switch is open, the current will flow here, pass through the 2 microfarad, pass through the 4 microfarad. Now they're asking, calculate the energy stored in the 4 microfarad. What is the energy stored in 4 microfarad? Now we got a problem. Is it going now 4 microfarad going to use 12 more volt? You can't use 12 volt because the voltage now will be shared by the 2 microfarad. 2 microfarad, 4 microfarad going to share the 12 volt. Who take more voltage? 4 microfarad take more voltage or 2 microfarad take more voltage? Anyone? Which take more voltage? Big capacitor take more voltage or small capacitor take more voltage? Anyone? How to know? What is same for both of them?
Charge.
What? Charge same. So when charge same, CV, C1, V1 must be equals to C2, V2. Right? So when the capacitance is for 4 microfarad, V1, the 2 microfarad, V2. So tell me from this, V1 greater or V2 greater? V2 should be bigger. Okay, V2 should be bigger. Small capacitance need a big voltage. So 2V1 is V2. 2V1 is V2. Okay. So here is V1, here V2. Okay, we assume V1, V2. We know V1 plus V2 should be 12 volt. Correct? V1 plus V2 must be 12 volt. Okay. We want to find V1 now. Our focus is V1. So V1 plus V2 is how much? V2 is 2V1. So V2 we replace with 2V1 is 12 volt. So V1 found to be 4 volt. So 4 microfarad, the voltage used is only 4 volt. The 2 microfarad use 8 volt. Small capacitance use big voltage. Big capacitance use small voltage to make the charge same for series. Okay. So this is the way you need to find what is the voltage of the 4 microfarad. So the solution is this open. Okay, so in this case is they are asking for the total charge also can. Okay. The Q equals to CV 16 microcoulomb So you can find the energy. Or you straight away can find energy equals to half CV squared can. So half C is 4 microfarad. V just now we got 4, so 4 squared. So also you get 32 microcoulomb. Okay. You find the voltage. The working show here, they find the total capacitance, then they find the total charge. So the charge flows in the 4 microfarad must be this 16 microcoulomb. So use half Q squared over C. Also can. Both method works. Any questions? So hope you understand, eh? No questions? Okay. That's all about capacitance. Okay. So what you learned so far? The capacitance? Today you learn about energy stored. When a capacitor is charged, V versus Q, the area and the graph is the energy stored. The energy stored got three formula: half QV, half CV squared, half Q squared over C. Okay. When you want to plot graph, basically the first equation is useless. Plot graph. Plot graph, use the second or the third. Okay, to plot graph. Energy versus V, energy versus Q. Use the second and third graph. First one cannot use because Q and V both are varying. Okay, just now from the PowerPoint we did this question. Okay, now your turn. Okay, this there is no working. You need to find the working for this. The answer given at the bottom here. Okay. Okay, again 2 minutes. Come on, guys. Use the entire knowledge you learned today. Not today, the entire capacitance knowledge, but especially the energy equation. Try to work out this. I give you 2 minutes. Try to get the answer at the bottom. 5 times A answer is 5 times 10 to the power negative 3. A answer got 2. B and C answer D answer. 2 minutes for you. Okay. So this is slightly a different question, different type of question. Two capacitor which was fully charged was connected to each other. What will happen? Okay, first I think A, I believe all of you got the answer. Okay, these two. 4 microfarad charge, potential difference is 50 volt. And second one, 6 microfarad, 100 volt. So what is the energy stored? The first one, I think energy stored, what formula to be used? A for the C1 lah. So C you know, V you know, so what formula to be used? Half CV squared lah, it's best. So you get the answer. So R 4 microfarad, 4 times 10 power of -6. V is 50 squared. So you get your answer, right? How much you get? 4, oh, this is 5 times 5, 25. 25 times 4. So 5 times 10 power. Do you get 5 times 10 power -5? 3. You should get this. So this for the one. E2 also the same thing lah. The half CV squared. You should get 30 times 10 power -3. The part A is easy. Part B is the problem. Okay, part B. The two capacitor was connected to each other like this. One is 50 volt, 4 microfarad. Another one is 100 volt, 6 microfarad. When they connected, the first capacitor has its own charge stored Q1. The second capacitor has its own charge stored Q2. Okay. When they connected, the charge will flow from which capacitor to which capacitor? And why? Anybody? The charge will flow from 6 microfarad to 4 microfarad or 4 microfarad to 6 microfarad.
6
Anyone?
to 4.
6 to 4. Why? High voltage to? Okay, so the charge will start to flow. Let's say this is positively connected, this positive, negative, 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 negative. What happened? Some charge from from negative plate of Q2 will flow to 1. Until the charge will flow until what happened? Until the both voltage become the same, voltage, and the uniform voltage. Okay, now the question is how much, which voltage, at which voltage the current stop flowing? Let's answer. What is the second is, what is the final common PD? This is the common PD. How to find this? What is conserved in this circuit? The charge. The charge, right?
Yes.
The Q1 plus Q2 is always constant for this circuit. Okay. So Q1, Q2 constant. Okay, this is the first equation. Okay. So find the Q1 and Q2. Okay. So next, when the voltage finally achieve the common voltage, okay, the new charge will be stored in both places. Okay. This is Q1 new lah, Q1 new and plus Q1 new. Sorry, So the voltage is same. C equals to Q over V, right? So V is what? Q over C. Okay. Because both have the common voltage, the Q over C for both capacitor must be same. So the Q1 new over C1 must be equals to Q2 new over the C2. Must be same. This Q1, Q2 is different than Q1 new, Q2 new. But what we know is the Q1 new plus Q2 new is same as the constant above. The total charge is same. Okay. Q1 new over first initial capacitance, how much? 4. 4 microfarad. Okay, should be equivalent to Q2 new over 6 microfarad. 6 microfarad. Okay. So this is your second formula. Q1 and Q2n is equals to the total charge. This is your first formula. This is your first formula. By using these two equations, you can find the Q1 or Q2. Once you know Q1, Q1 over C1 will give you the voltage. Okay. So first, what is the Q1 value? What is the total charge? Can you calculate the total charge for me? What is the total charge? What is the Q1, Q2 charge? Q1 how much? Q1 is CV, right? CV, the original voltage, CB, C times V. Yeah, CB. So 50 times 4 microfarad. 20 microcoulomb is your Q1. Q2 is how much? 100 times 6. So it's 600 microcoulomb. Q2. So Q1 and Q2n total should be 800 microcoulomb. First equation. Okay, can you find now Q1n how much? You see, you have the first equation here. Q1n, Q2n equals to 800. Qn over 4, Q2n over 6 is the same. So can you find? It's a simultaneous equation, right? Okay, let me show here, no space. So here, so Q1n over 4 equals to Q2n over 6, second equation. Q1n plus Q2n equals to 800. We are looking for, this is the first equation. You're looking for V. V we know is Q1n over C1 or Q2n over C2. So if you know Q1, Q2 or another one of them, you can find the voltage, the final voltage. This is a common voltage. Okay, so from here, can you find the Q? So from above, second equation. We found 3Q1 2Q2 to N. N. So Q1N is found to be 2/3 of the Q2N. Okay. So here in the second equation, Q1N we throw out. So we put 2/3 Qn plus Q2N. This all are 2N. Is equals to 800. So 1/2 Q2N is 800. So Q2N how much? 800 times 3 over 5, right? 3 over 5. Anybody got the answer? Q2N how much? How much is this? 800 times 3 over 5. 2400 divided by 5. 480, right? 480 microcoulomb. Correct? Yeah, 480 microcoulomb. So what is the common voltage? Q2N over C2. Q2N is 480. C2 is how much? C2 is how much? C2 is the 6 microcoulomb, right? So 6 microcoulomb. How much you get? So 80 volt. So this is your common PD. Okay, so this is the working. So B is a little long to understand. So try to understand the concept. When two charge capacitor was connected, the charge will flow from high potential to low potential until the voltage becomes same. So achieve a common potential. Okay. So what is conserved? The total charge is conserved. So Q1, Q2 is the original Q1, Q2 original charge. You can find the original charge by using 54 and 106. The original charge found to be 800 microcoulomb. When the charge go and rearrange, we get a new charge stored in Q in Q1, Q1N, Q2N. But Q1N plus Q2N still should be 800. Okay, the total charge is never changed. So Q1N, Q2N is the first equation, 800. But Q1N over C1 must be equals to Q2N over C2 because common voltage same. So by using these two equations, we work out the Q1 how much, then we substitute back in the voltage formula to get the common voltage, and to get a common voltage, 80. Okay, any part you don't understand? This is something tricky one. And two capacitor charge connected, what will happen? This is what will happen. So any part don't understand? Yes. So what do you do? And two capacitor connected, you find the total charge first. Total charge what? And then when the charge newly arranged, the Q1N, Q2N must be the total charge, one equation. The Q1N over C1, it should be equals to Q1N over C2 because common voltage. Use that two formulas, simultaneous, get the Q1, substitute into the Q1 or Q2 lah, anyone you can find. You can find a common voltage. Okay. So you can take down. Okay, any part you don't understand? Okay, so I hope you understand. Okay, I go down. So the common voltage is found to be 80 volt. Answer for B. Okay. Now they ask, what is the energy stored after the connection? Now, what is the new energy stored in both capacitance? Now you know common voltage is 80 volt. You know the capacitance is 4 microfarad and 6 microfarad each. So you just use half CV squared, right? Half CV squared. Half CV squared. C for 4 microfarad, you just put 4. V, you put 80 squared. And you get the energy. Energy is found to be 32 and 3 times 10⁻³ joule for each of them. Okay. So I think C and D not a big not a big problem. What is the energy stored after the connection? So the two capacitor energy, you add them together, you get the total energy. 32. 32 times 10⁻³ is the total energy. Okay. So what happens to the difference in energy stored? You see, initially, how much is the energy stored total? 30 plus 5, 35. What is the energy stored after connection? 32. How much energy differences? 3. 3 times 10⁻³ joule. What happened to this energy? Lost in the connecting wires. That's the blame you can say. Okay, any part you don't understand about this question? No questions. Okay, so we're done with this topic. You go and try to do these questions. Okay, at the back you have questions. Try to go ahead, and you have a mark scheme. Try to understand further. Okay, so next class tomorrow we'll be discussing some question, maybe 20 minutes now. We'll be discussing the passier, electric field and capacitance. That day we did electric field, so now we do capacitance from that paper, about maybe 20 minutes. Then tomorrow we start with a new topic also, magnetic field. Okay, guys. So we stop here. Any questions? No questions. Okay. So see you then. Bye.